All right, I'm going to spend the next few minutes sharing with you a portion of the research that we published last summer in Water Resources Research. And the title is a little nebulous, but that's a good way to get picked up in a lot of literature searches, right? So when we think about the history of riparian salt cedar control for decades, at least since the 40s, millions of taxpayer dollars have been spent treating salt cedar along rivers in the southwestern United States, with the primary goal of what? Increasing stream flow, right? Because early unsubstantiated reports indicated that these trees could use up to 200 gallons of water per day. And a couple of my co-authors on this paper published a great paper that demonstrates that that is physiologically impossible. Okay? More recent estimates using SAP flow methods, energy budget methods, indicate that the water use on a stand level is about a third of a meter to 1.5 meters per year. That's substantially less than potentially evapotranspiration and substantially less than open water evaporation, which is probably about 3 meters per year in most of these areas. No projects that I'm aware of have ever demonstrated an increase in stream flow. Typically, they report an estimate in reduced evapotranspiration or reduced transpiration, no demonstration of an increase in stream flow, nor a demonstrated increase in aquifer storage. But why not? It's perplexing, isn't it? It seems logical that if we kill a plant, any plant that we know is accessing stream flow or groundwater, that on a large scale there must be some obvious savings. Well, I'm going to walk you through a case study along a semi-arid river that will provide some insight. And the semi-arid river that we alluded to is the Pecos River. The modern-day headwaters of the Pecos River are in northern New Mexico, near the town of Pecos. It flows along the eastern half of the state and into Texas. The Pecos River is really the only major tributary to the Rio Grande in Texas. There are 4 dams in New Mexico and 1 right at the state line in Texas. So we had a really unique opportunity to look at the impacts of a large-scale project. The Pecos River Ecosystem Project was conducted along the Pecos River in Texas. And this is a low-level aerial image near the state line, just into Texas, south of the New Mexico state line. You can see it's a very sinuous river with a narrow riparian zone. And the major emphasis of the project was an aerial herbicide application using a helicopter. And it was extremely effective. Over a period of years, they treated about 10,000 acres and almost all of the length of the Pecos River in Texas. Both sides of the channel, much of the channel, and some major tributaries as well. And the project was extremely effective. They achieved over 80% mortality, which is very high for a large-scale brush control project, especially an aerial application. So that gave us a unique opportunity to look for this signal in the stream flow. Unfortunately, our hydrograph analyses indicated that there was no detectable increase in stream flow. So we struck out again. Surprising. Well, looking at the large-scale hydrograph analyses, we didn't find a signal. So we thought, you know what, we're going to go to the really small spatial and temporal scale and try and tease this apart. Take a really close look. And this is a picture of our study area. We had about a 3-kilometer reach of untreated salt cedar where we conducted this portion of the study. And you can see just for scale that our plants are quite large. They are multi-stemmed, but they're quite large and they appear to be quite old. We don't know exactly how old they are. And what you'll notice here from this other low-level aerial image is that the riparian zone is very narrow. The channel is quite in size, which is not unexpected considering that it's a highly regulated river. So as you move from this narrow riparian zone, you quickly uh, move out into the abandoned floodplain, which is very xeric vegetation. Four-winged saltbush, honey mesquite, a few perennial grasses, and low-lying areas. The elevation at this study area is about 820 meters. Annual rainfall to 70 millimeters, about 10 inches. So for those of you who might not be familiar with this system. The aquifer here is a very thick alluvial aquifer of Quaternary age. Lots of variability in vertical hydraulic conductivity, as you would expect from a floodplain aquifer. So the hypothesis we were testing is basically that if transpiration indeed impacts stream flow and groundwater, that there should be some signal manifest in the stream stage and groundwater levels that's opposite of transpiration signal and probably lags behind that somewhat. So let me show you what I'm saying there. Essentially, we know that transpiration increases during the day to some maximum as vapor pressure deficit increases, and then it begins to decline to some minimum at night. And it does this over and over again, fairly predictably during the growing season. What we would expect, if there's a strong coupling between transpiration and water levels, is that we would see a signal in the stream stage and groundwater that would be opposite the transpiration signal, and that it wouldn't be instantaneous. There would be some time lag between maximum transpiration and maximum decline in water level for each day during the growing season. So our approach basically was to take these very detailed measurements, and what I'll be sharing today are data from June of 2004. June is at the height of our growing season. The plants typically begin to leaf out in April, so by June they're fully leafed out, and we have very long days. So we expected transpiration to be at maximum levels for the season, or at least representative of near the maximum. So we looked at transpiration and water levels and basically used some statistical analyses to really characterize those diel cycles and assess the coupling between transpiration and water levels. We used the heat dissipation technique that was kind of not originated by Grenier but refined, and my colleague Georgianne Moore is a plant physiologist, and she really was the lead on this portion of the project. But essentially, you insert sensors into the xylem tissue, and this one records a background temperature, and this one also has a heat element attached to the sensor. And so based on the temperature difference between these sensors, we can compute the amount of heat dissipation or sap that is moving up the xylem tissue. We instrumented 9 trees in a 238 meter square plot, and temperature measurements were conducted every 30 seconds and averaged over 30 minutes. So when there's essentially no sap movement, which we haven't found that to occur, but the maximum heat difference occurs when there's when sap velocity increases. Okay, so we had 3 trees near the channel, 3 in the center, and 3 along the edge of the abandoned terrace. Our 9 censored trees. In addition to the sensor measurements and to allow us to assess sap velocity, we have to know Sappwood area to compute the volume of transpiration. Within that 238 meter square plot, there were 61 salt cedar trees. We harvested all of those to get an idea of how much sapwood area or xylem, active xylem tissue there was in that plot. And again, I'm not a plant physiologist, so this was really intriguing to me to note that as these plants mature, they develop these lobes. And so the sapwood area is delineated by these red marks. All of this in here is dead heartwood. So for any given tree, and the average diameter of our trees was about 6 inches, or 16 centimeters. Only a fraction of that, of course, is going to be active xylem tissue. In fact, what we found is that the Sappwood area within that plot was very, very small. In fact, 0.0007 meter square of Sappwood area per meter square of ground area. What that translates to kind of get your head around that, is 1 square inch per 1 square yard of ground area. It's very small. So shifting to some of our water level monitoring. We have a network of monitoring wells at several locations. At the time of this study, we had 3 wells within the riparian zone, a stream stage recorder, and 1 well out in the floodplain. Essentially, this is what the cross-section looks like. So we have our stage recorder, wells B1, B3, and B2 under the salt cedar canopy, and then this B5 out here in the abandoned floodplain. Okay, so to move quickly into our results, here is calculated transpiration. This is hourly transpiration for the month of June. So from midnight to 11 p.m. for every single day in June, there's 700 points here. And this is transpiration in millimeters. And what you'll notice immediately is that we get this nice diel signal, this sine curve that we would expect. Minimum transpiration typically occurred between 4 and 6 a.m. and maximum between 3 and 5 p.m. You'll notice that nighttime transpiration does not go to 0, but there's much less variability at night. And also that quite a few of our daytime data points overlap with our nighttime data points. These are hourly data. Our mean daily transpiration was about 0.3 millimeters. And not a huge amount of variability, 0.29 plus or minus 0.2 millimeters per day. This is the hydrograph for the whole month of June. Here we had the water elevation converted to meters above sea level, and transpiration on the secondary axis, or precipitation on the secondary axis. These are the few storm events that occurred during the month of June. So the first thing you'll notice is that the stream elevation was always higher than the aquifer, which means that it's a losing stream, right? Second thing you'll notice is that the riparian wells, they're all a similar elevation, what you would expect. They're really in a triangular configuration so that we could construct flow nets, which was another part of the study. And then you'll notice that B5 is much deeper. As we move from that incised channel out to the floodplain, the depth to groundwater increases rapidly. Okay. Another thing you'll notice that probably stands out is, oh, we have the same diel signal, the sine curve in B3, and you can also see it in the stream, but it's much more faint. It's absent in these other wells. So kind of bringing that transpiration data and the water level data together. These are all time series data, and so there are certain statistical analyses that allow us to really assess those cycles, kind of tease them apart, look at the frequency, the duration of the cycles, and the first step in those time series analyses essentially is to determine if there really is a pattern. So it's a more subjective way to look at that hydrograph data, for example, and instead of saying, oh, that well B3, it shows the same pattern as transpiration, salt cedar must be causing that. Well, an alternative is to conduct a white noise test, which determines whether your time series data really exhibits a pattern or if it's random white noise. Of all of the data sets, only the transpiration, the stream stage, and that well B3 were statistically different from random white noise. We discarded everything else. Then we conducted Fourier transform or spectral analysis to look at the frequency and duration of the cycles in transpiration, stream stage, and well B3. And this is just an example of the periodogram for transpiration, which basically we look for these peaks, something that makes sense biologically or physically speaking. And in this case, this is transpiration, and it shows that there's a peak at 24 hours, which is logical, and that's good. Same basic pattern for well B3 and the stream stage. So then we decided, okay, we know there is a pattern. What is the coupling between transpiration and the groundwater and stream stage? And we thought that probably would be characterized by a time lag. So if they're coupled very closely, there would be a much quicker response in stream stage and groundwater. And we basically did a really simple Spearman correlation calculation to look for those time lags. So we did it at 1 hour time steps, taking the maximum hour of transpiration for each day in June and determining when the maximum decline in groundwater level or stream stage occurred. And what we found, these solid dots are the groundwater, is that maximum decline in water level occurred about 7 hours after maximum transpiration, and maximum decline in stream stage occurred about 17 hours after the hour of maximum transpiration. Well, we were a little bit surprised. 7 hours, well, that seems plausible perhaps. 17 hours, it doesn't seem like there's much relationship there. Very weak relationship. So to take it one step further, we computed a regression analysis with the transpiration data, of course, as the independent variable, and those groundwater and stream stage measurements shifted by 7 and 17 hours respectively, to look at a little bit closer at that relationship. So we were kind of disappointed. This is transpiration, change in water level. Here's 0, so essentially no change. And this is a decline in water level, and this would be an increase. What we found for groundwater was an R-square of 0.16. So really poor. I'm not a statistician, but one way to interpret that would be that hourly transpiration accounts for about 16% of the variability in groundwater fluctuation, and only 0.0045 for the stream stage. If there was a really strong relationship, we would expect to see a pattern in the data like this. As transpiration increases, we get these greater and greater declines in hourly groundwater or stream stage. Okay? So what do we attribute this to? Well, in our case, on the Pecos River, we attribute that to very low Sappwood area and low sap velocity. And that primarily is a function of plant age, size, and density. And Ryan did a really nice review of about 51 different woody species. Salt cedar was not included in those, but surprisingly, apparently plants are very much like people. As they age, their resource demand typically declines, and that's a function of leaf area, sap velocity, sapwood area, per basal area, the very characteristics that we observed in our stand. And plant density as well. Our plant density was about 2,500 trees per hectare. And we had a companion site on the Middle Rio Grande at the same time. Plant density there was about 10,000 trees per hectare. But they were very young, actively growing plants with very small stems. Taking that from the small scale to the large scale, why are we not seeing this impact on stream flows? Because that's really what all of these projects have been aimed at, or at least many of the early projects. And we attribute that to a very narrow riparian zone on the Pecos River. When you compare that, for example, with the Colorado River, which can have a quite expansive floodplain, to the Middle Rio Grande with a floodplain as wide as 10 kilometers, it's just a very narrow strip in a very large landscape. It's difficult to tease out these small components of the water budget. Transpiration to stream flow, that ratio also is really important. For example, on the Pecos, we saw such a weak relationship. Well, our transpiration was 0.3 millimeters per day. Our stream discharge was 8 to 12 cubic meters per second. It's like looking for the proverbial needle in a haystack. Conversely, some colleagues of mine in the H.J. Andrews National Forest found a very, very tight coupling between riparian transpiration and stream flow. Well, just the magnitude, Doug fir was the dominant species. Transpiration there was an order of magnitude greater, but stream flow was minuscule compared to ours. So that coupling or that relationship is much more easily detected depending on this ratio. So the conclusions basically are transpiration was very weakly coupled with groundwater at our site, essentially no impact on stream flow. And we attribute this again to the fact that transpiration was a small component of the water budget. So it's really important when thinking about these large-scale projects and what the impacts might be on the water budget to at least know the relative magnitude of each component. And then that will give you some idea about whether there's any hope for detection. And I don't have these people's names here because you're never going to see them, but just to give you an idea that, lots of people contributed to this project in addition to the co-authors. And I will leave you with a last photograph. We had a major flood event in September of 14 on the Pecos River. It was outstanding, truly. But now we're left with all of this woody debris. This is dead salt cedar, the channel. And as a lover of fluvial geomorphology, woody debris is not a bad thing, but some people are really upset about this. So that could be an unintended consequence. All right. And I think I might have used up my question time. So, absolutely. Yeah. Thanks. Yes.
Native species? I know you didn't measure it, but
I would say that is highly likely that native species that we would see the same relative magnitudes in the water budget, yes. Yeah. Georgianne Moore is my colleague who is the plant physiologist, and according to her, there is nothing about salt cedar that indicates that it is a flagrant water user. Most plants are not. And transpiration is driven by atmospheric conditions. Plants are just a conduit. They have strategies to limit that, but it's a physical process, not a biological.